Welcome to a new episode of Randomly Typed. I'm JS.
Hi, I'm Lance.
You're listening to a free podcast. Woohoo!
Oh my gosh, free as in beer?
Free as in Creative Commons.
So free as in freedom.
Free as in freedom.
Awesome.
So now we decided to release our podcast as a Creative Commons 4.0 attribution something. So this means that you can use our podcast as long as you attribute it back to us.
Go check out the website for the details. There's a badge at the bottom, so you can read more about that if you like.
Yes.
Last podcast, I was very clueless about the fact that I don't know anything about reverse engineering and its legality. I mentioned that it was good that I mentioned I wasn't a lawyer because what I said was completely off base. It seems like in most countries, in most jurisdictions, reverse engineering software is illegal except for in very specific circumstances.
Like what?
From what I read very quickly, we could maybe do a follow-up episode on this because it's generally interesting, I feel like. Things that are kind of meant to be public by default. Things like known APIs. I know there was the Google Oracle debate, the Java that was going on as well, so that might play into that. But that's like a dubious case. So again, I'm not a lawyer. Please do not sue me. I don't know what I'm talking about. I would plead insanity anyways. If you are interested in reverse engineering things, go follow up on the legality of the situation.
Because by default, it's mostly illegal.
It would be a good default to have.
All right. What's the real subject today?
So today we're going to be talking about data structures. This one is one I like. These are fun data structures.
Is there some boring data structure?
There are some boring ones, yeah. So today we're going to be talking about immutable data structures. Both fun and boring simultaneously.
All right.
What are your opinions on that, Jess?
I like to use immutable data structures because they give you some promise that you normally don't get. It's easier to get a sane program that doesn't have some sneaky bugs.
Yeah, it imposes a bit more constraints on what you can do with this particular data structure. So it could be more predictable in some senses. So what are we even talking about? Immutable data structures, or persistent data structures, they'll sometimes be called. I like to think of them as append only. That's not necessarily the best description of them, but things within the data structure that you've written to before are immutable and cannot be changed. The only way of changing the representation of those previous values is by adding new ones and effectively hiding the old ones. One nice thing about immutable data structures is that they keep their representations of all modifications to this object throughout time. So you can kind of reference into a specific moment in time, or like at a specific moment of the life cycle of this data structure, these values were there, and you have the guarantee that it's immutable at that state.
It's really interesting. It gives us features like time travel, or to make sure that at that time the data was correct. So going back in time to see how it was at that point.
In a sense, yes, you would need to have references to all previous times, though. What's very clever about these data structures is that if you're given a reference to this one object, it has this representation that you can explore. It has data within it, but it does not allow you to access things in the future, like future modifications that were done, because you would then be able to be accessing data that may not
exist at that point.
That and or was not destined for you to see, in a sense, right? Someone else said it, so they kept their reference, and unless they share that reference with you, you cannot see their data, right? It is a slice in time. So if someone else did something to this data structure, you don't necessarily have access to it.
So, but this is only true as long as you don't like go read the direct data structure byte by byte and try to interpret it, right?
Well, what's clever about this is that you can't, right? You're unable to read things in the future that someone else modified. This is why this is attractive, because if someone else modified this data structure, they have a completely new object that is appended on and relies upon previous objects. So if you only have a handle to the reference, it's like unidirectional. You can't go see what someone else has unless you have that reference.
Sure, but it's not cryptographically secure. Like if someone hacks my computer and have access to one of the reference, I'm sure there's a way to get the other ones, right?
I mean, they're in memory, yes. They're in memory, but it does give you a guarantee that, like, let's say from one specific stack frame, if you're further into the stack and a modification was done and that reference wasn't passed back to you in any way, you can't access those.
Right. So
right?
in normal use cases, you don't have access to them.
You could say so, yeah. So every individual modification that's done it throughout time is kept as long as you keep a reference to that representation. There are things called partially persistent data structures, and those are ones which only let you modify the latest thing. So the latest representation of this data structure as a whole is the only one that can be modified.
So it's like immutable except the last slice or something like that?
So the whole thing is immutable, but it can't be grown. You can't add on to this data structure unless you're at the last slice.
Okay.
Do you think that would give any useful properties?
It kind of represents time.
Yes.
So if you're back in time, you cannot rewrite time.
That's exactly it. So this represents a linear ordering of events.
Oh, right.
You don't have the ability to create branches in time or have multiple timelines. That exists in a data structure which is called fully persistent. So it's always, all versions of it are always there and able to be branched off from it.
Okay, so like a little bit like Git?
A little bit like Git, yeah. Like unless you kind of go the extra mile to ensure that it's only partially persistent, most things you can kind of just like grab any representation and build off of it.
Okay.
There are other ones called confluent ones too, and what that means is you have basically merge back into a Git branch. If you have two separate data structures and you can kind of union them in some special manner, then you can call it confluent. But I'm not too familiar with those, so we can skip right over those if you like.
But what would be the use case?
Well, like Git, when you've created an alternate timeline and you want to merge back in, right? That's a data structure that's able to make sense of two separate branches and union them back into one.
Oh, wow, that's nice. All of those sound really good for concurrency, right?
Yes. So that's actually, I was going to ask you, why do you think these are useful? And that's probably the number one use case. They handle concurrency very well. Why did you say that, Jess?
Because you're always sure you won't modify something you shouldn't be able to modify. And one of the biggest source of bugs in concurrency is modifying something that someone else is modifying or reading at the same time.
Right, exactly. So every write is happening to a completely new object. It isn't writing to an object that might be shared with other readers, let's say. So it avoids that class of bugs entirely. Of course, you can write, but that's being done to a separate object in memory, and the values that it depends on are not being modified, right? It's append only in that sense. So you can still like build things, you can still do something with this immutable data. It's just that if you've modified something once, you can be sure it'll never change. So it's very useful for concurrency. And can you think of one other reason why it's useful?
I know some database uses it for like their source of truth. For example, like Redis is append only log. So I feel like there's some security into being able to save the previous state without like corrupting the state in the middle of a save or something like that.
So that's also one. That wasn't the one I was going for, but it's true that if you have like kind of like the ordering of events in a system, you can kind of recreate your system afterwards. You can basically have like an audit log of all the things that happened. What I was going for is it avoids situations where you need to do something like copy on write for a big data structure. Let's say you had a giant hash with thousands and thousands and thousands of things, and you needed to do a copy of this if you were to copy on write to ensure that you have these same concurrency guarantees. Then it avoids you from copying the entire data structure. All these do is build on top of existing ones. Never do any copying.
So you don't need to copy at all. That's what I say.
No, so it's how it works is something called structural sharing. So it uses the previous data structures as a base to build upon. So every time you add something new, it still references the old one. You never copy all of those to a new spot. They're just still there in memory. It's just that it points to them via a reference.
Right. Do you have some concrete example of those data structure, or do you don't want to go there?
We can go there really briefly, but we're going to go there in much more depth later on. So later on, we'll build an immutable hash map together.
Oh, wow.
And it has a lot of advantages to using a non-immutable hash map, as well as some disadvantages. But one of the advantages is that you can build it iteratively, right? You don't need a giant slab of memory in advance and a giant buffer to fill your hash table with. You can kind of build on top of existing structures as you add keys. So you don't necessarily, like, if you fill your buffer for your hash map, You don't necessarily need to allocate a new one, copy over all the existing values, and then start using that one. You just always keep the same references to the same original objects. There are never any copying.
Right, but I guess in a read-heavy situation, that could be problematic because like having all your memory in the same space is good for the CPU, right?
Yeah, well, good for like cache line efficiency. Yeah, well, that's always hard to measure anyways. But yes, so I mean, advantages and disadvantages, but that's one advantage of using this kind of data structure where it uses the same structure to build upon itself. There's never any copying of super big chunks of memory with the same values into another spot. There's two good ways of building these generally. We can maybe make this a bit more concrete. What's the simplest data structure that you can consider immutable that you can think of?
Well, anything that you cannot change, so like an int that you're not allowed to change.
I guess that's like a hack. What kind of like container could you have in which you could like have operations be done on it, which holds other things?
A pointer.
I was going for something like if you had an append-only log or like a singly linked list where the only operation is add.
Right.
That's a good example of an immutable data structure where all of the nodes are there on already existing. And every time you add a new one, you add the new node, but have it refer to all the previous old nodes. Right. So in that way, there's never any copying. It's more just progressive enhancement of this original data structure.
And if there's like two threads doing an add at the same time, they both only have like their last pointer. So there's no conflict. They have their own version of reality.
Right. And that the first one would not be aware of the node that you added afterwards, let's say.
Yeah, exactly, because it's the new node that points to the previous one.
Right, because they have different references. Mm-hmm. So how you can do this, there's usually two ways of doing this. One of them is path copying. So that's kind of what we were alluding to just now, in which you add a new node and you have it reference all the old nodes. That general strategy of building this data structure is one in which the new value in your data structure is represented by a new node, and all you have to do is figure out the connections to point it to the old nodes in the right way so that you can still access all of the old nodes.
Okay.
The other alternative is something called fat node. So what you do is you keep all of the edges and you don't make any new nodes, but you store all the values in the individual like leaf nodes, let's say.
I don't get it.
So one example, let's pretend we're making an immutable hash map.
Okay.
One strategy for if you add a new key is to make a new node that represents this new key and associate a value to it, and make sure you're able to fetch all the other ones through adding edges, basically.
Okay.
So that they're still accessible. The fat node version is if you set the same key 3 times, then you only have a single node which represents that one key, but 3 values in it, and you're able to distinguish like by what reference you have or what reference the caller has, what value it is, or you have some way of versioning the values that are in this singular node.
Okay. But this is not immutable because you had to modify the container, right?
Internally, it's not immutable, but from an external perspective, it seems immutable.
Oh, okay. So when we say immutable data structure, we don't necessarily mean that this data structure itself is immutable?
I think it's a good principle to follow, and that's why I think most that I've seen use this path copying version where they just add a new node and have it reference the old ones, right? It's kind of more conceptually aligned with what you're trying to build, I feel like. So now that we know all about these, let's try to build a hash map or associative array, people call them as well. There are like a million different names. If you're from Python, it's a dictionary. If you're from Ruby, it's a hash. There's maps generally. Associative arrays in PHP.
I never heard this one.
So that thing, right? The thing where you have a key that you assign a value a key, and you can retrieve a value based on the key and set a value based on that key.
All right.
A big table, basically.
Key value store.
Sure. That also has other connotations, right? But yes.
Sure.
That thing to the listener. I know you know what I'm talking about. I'm just trying to make sure that everybody knows what I'm talking about. So let's build that. How that's built normally is you have a big array, basically, and you use a hash function to hash your key.
To know where to put it.
Which represents the index in your array, right? And then you just plop the value at that index.
Right.
So let's do that using something called a trie. Have you ever heard this before? Or a prefix tree?
I heard the name, but I have no idea.
Like trie is like TRIE.
Okay.
So you can build something very similar, and you don't have to hash the input, the key in this case. So how this works is, imagine you're trying to insert the key value pair of ABC and 1 into your immutable hash map.
Okay, so the key is ABC and the value is 1.
Yep.
Okay.
Well, how a trie works is it splits your key into individual letters.
Okay, so A and B and C.
So in order to arrive at the value 1, which you're searching for with the key ABC, what you do is you add a node into a tree, which is A. So at the top level of your tree, you have the A node. So you have the root node, and then at the next level, you insert a node with the key A.
Okay.
That's the only thing it has. And then from that node, you add another node, which can be accessed at the next level down of B. And then from that, you have another one, which is C. So root node links to A links to B links to C. And then finally in C, that last node, you just add a value to it. And that value is a 1.
All right. That's interesting, but why is it useful?
So the way it's useful is that now let's say you want to add A, B, D with the value of 2.
Mm-hmm.
What you can do is you start at your root node and you say, let's add A. Oh, wait, A already exists. It's already here. So let's follow that path. Now let's add B. Oh, B already exists. Let's follow that path. And now, is there a D? No, there's no D. So let's create that node with the key D and associate the value 2 to it.
Right.
So you didn't have to make a whole new series of nodes every time. You kind of borrowed what you already had when you could. And this is why it's called a prefix tree, right? So like the A is the prefix of your key, and then AB is the prefix of your key, and that leads you down this path of this tree to find your value.
Right, I see. But what's the property of that data structure? Like, is it fast? Is it memory efficient?
As with every data structure, it depends. In some cases, you can have less memory consumption.
Okay.
Especially if you have short keys or if you don't have a lot of values. And that's because in a hash, you need to allocate an array of a certain size in advance. This you can do progressively. So if you only have one value with a one very short key, you can only need to allocate one tiny object to hold that value.
And I guess not having to hash the key is interesting.
It is. You can also build this with hashing, but then you need to figure out how you're going to deal with hash collisions, and it becomes more similar to a regular hash map in that regard. One neat hack is that there's an alternative data structure which is basically the same thing called a radix tree. It's identical in nature. It's just that instead of allocating a new object for every new node along that thing, you can just compress them all. So you can have the AB node and then C and then D.
Okay. So it's like the next level of
Right. It's just like compressing useless nodes which don't have any values associated with them.
That sounds like a good optimization for data structure that are weirdly set up, like that have super long keys that are not useful.
Yep, exactly. So again, you could also have more memory consumption though, because you could end up having more nodes, which make more space, whereas this is handled with hash collisions in a full hash map, right? Mm-hmm. So like they'll both hash to the same value, and you just have like the values. Right. They both hash to the same index, and you just have the values there. Another advantage is that it's a bit more structured. So if you wanted to use an application where you're like, give me all values where the key is less than KA lexicographically.
Right. You can do a search from that tree.
From that, and then just have all of the nodes be sorted or go through all of them and see which ones apply. Whereas in the hash map, you have to literally look at every value in all of your...
Because you never know when you're done.
Exactly. Actually, you know what? Whereas in a hash map, you actually cannot do this because you've hashed your input.
Yeah, so you would need to reverse the hash, which is technically impossible.
Yes, exactly. So you can't provide that kind of information. So it's useful for things like full text search. Right. So if you want to like find all the values that begin with HA, now you're able to find all of these values and all the words that begin with that. As a disadvantage, it's a faster lookup in the worst case. So in the absolute worst case, where everything is a hash collision in your hash map, then it would be ON, right? So in this case, in the worst case, it would be faster to use this data structure. But on average, it's slower, right? Because usually hash is pretty fast to calculate your index, and you just go directly there. And the chance that all of your inputs hash to the same value and all of them had hash collisions is pretty low. So now we know how to do tries, or prefix trees. Making the immutable version is actually super simple. So we had ABC1 before. So then we have the root node, you go to A, you go to B, you go to C, and then with the C node, you associate the value 1. In a regular trie, if you wanted to add A, B, C with the value 2, you would follow this same path and then just replace the 1 value. In an immutable hash, you can't do that because it's immutable and someone else could be looking at that or have a reference to that, and then the value would change from under them. So what you would do is you would make a new root node, completely separate root node, so that your reference to the new modified version of your immutable hash is that root node and not the other root node. You have to keep the other root node around because someone else might still be referring to that, but you make a new root node. You add A, B, and C. So in this case, these two graphs are not linked at all. They're completely separate in this case. But if you had the previous case we talked about, let's imagine now we had a data structure with ABC1 and ABD2. When you're setting it, you get a new value back, so you still have access to the old value. You would have to traverse your tree as you're making new nodes for your new value that you just set. But if at any point you come across something that is not reachable by the value you're currently setting, so any key that is not ABC, you need to point towards in your new root node. This is a little complex. So let's say we had ABD in our first one, and we're trying to add the value ABC to a new immutable hash. You would have both hashes, the old one and the new one. You could say, okay, well, is there an A in the old value? Because I know there is going to be one in the new value. There is an A in the old one, so I don't need to reference this node. I still have all the information in my new one to be able to access future nodes.
So you just keep the difference.
Basically, you keep the difference, yeah. And then you do the same thing. So now that you're at the A node, you look at the next nodes, the next child nodes of that A node, and find all of the ones that are different from the one you're about to add.
Right.
So in this case, there would be none, actually, again. So A, B are present in both. So you don't need to reference any of the previous nodes in the previous tree. But here is where you would start referencing, right? In your new one, you're trying to do ABC, and in the old one, you're trying to do ABD, let's say. If you're at the B nodes in either tree, the new one is about to be C, the old one is D. That's a different value, right? And you want to be able to access the old values as well as your new values and share that structure. So that's where you need to make a new edge from B to D so that you're able to access that old value while still creating your new value to associate the new value to it.
Right. And it's only accessible from the new hash.
Exactly, right? Only accessible from the new hash. The old hash doesn't have this reference, this new node that you've added for your own value. They do have all the references to the previous nodes, though. So every new layer, every new modification makes a new layer of nodes so that the value that you've just said is accessible to you, but it makes edges, unidirectional edges, to all of the other nodes in the previous trees so that you're still able to access them.
That sounds kind of inefficient.
It can be, and I know there are lots of optimizations for this. This is kind of the one I've just thought through alone. I know you can compress a lot of the middle nodes, like in the radix trees. They're like binary. You can represent these nodes in binary and do like bit shifts, if I'm not mistaken, to be able to figure out which value it is. There are lots of optimizations you can apply here. But just conceptually, that's what's happening, right? You're adding a new node that's only accessible to you while still being able to access all of the old nodes. And the old references, not losing any of their nodes.
Nice.
So that's it. We just did it. We built a new immutable hash data structure.
How do you call it?
Immutable hash data structure.
Original, Lance.
Yeah. If there isn't, I'm sure there's already a library in your favorite language of choice to do exactly this. If there isn't, now you know how to make one. It might be a little naive of an implementation, but it'll work. That's the inner workings of it generally.
Nice. As we said, I should use that when I'm doing concurrency?
Concurrency, or if you want to keep this immutable nature of an object, but don't want to have to copy everything over.
Right.
Those are two good use cases for this. Or if you just want like some nice encapsulation and information hiding, and that you can like add a new reference, you keep that reference, but nobody else has it. So it's a good way to encapsulate data that's not necessarily shared across all objects in your system.
Do you have something else on the subject?
Nope, that's all for today.
Interesting. Well, thank you, Lance. That was really enlightening.
Thank you for letting me ramble on about data structures for, I don't know how long, 30 minutes maybe?
Well, before the cuts, 31 minutes.
Okay. Thank you for letting me do this, JS.
No problem. All right. See you in 2 weeks.
All right. See ya. Bye.
You can contact us and find show notes on our website, randomlytyped.com.
The intro music is by Vansky.
Thank you, Vansky.
And thank you, listener, for indulging us.